Then welcome for another installment of the Quantum AI speaker series. Today it's our pleasure to welcome Guilhem Semerjian, who is here with us from France. He is assistant professor in the École Normale Supérieure in Paris. And that's also the place where 10 years ago, 2004, he got a PhD. In between, he had a stint in Rome at La Sapienza for his postdoc. And Guilhem is focusing on statistical mechanics methods, mainly applying them to various fields in discrete mathematics and computer science. And a particular interest of his is applying it to random constraint satisfaction problems. And recently, I think, or not sure how recently this was, you also have become interested in the role of quantum fluctuations within the adiabatic protocol, which role they could play helping to solve constraint satisfaction. So I'm looking forward to your talk.
Okay, so thanks a lot for the introduction and for the invitation. I am very glad to be here today. So I will indeed try to tell you a story of a field of interdisciplinary research which has taken place at the crossroads between theoretical computer science, discrete mathematics, and also statistical physics, which maybe is the surprising part of the interface between these different fields. So as I was invited by the quantum group, of course there will be something quantum, but only at the end. So the talk will be, I think it's important first to understand what goes on in the classical case before tackling the quantum one, and I think it can be interesting for a wider audience, the story about this random constraint satisfaction problem. So as I said, it's an interdisciplinary work and an interdisciplinary story, and I guess this is also in an interdisciplinary audience. So I will try to speak to all of you, taking the risk of speaking to none of you, but that's a chance I will take. So, okay, for the people here, don't hesitate to interrupt me if some things are not clear, and I will try to get you all on board. So I will first recall what are constraint satisfaction problem, and then motivate and define the introduction of random ensemble of such problems. And then I will describe quickly what physics and statistical mechanics methods has produced as results in this for this kind of problems, and finally I will touch upon the effect of quantum fluctuations on these problems. So, constraint satisfaction problems are defined in a, let's say, very simple way. So imagine you have a certain number n of variables which can take a finite number of values, and so they are in a discrete alphabet. And for instance, you can think of Boolean variables, true or false, or 0 or 1, as you want, or if you are a physicist, plus or minus 1 as Ising spins. And then you add some constraints on this set of configuration, and the constraint is some function of a subset of the variables, which can be either satisfied by this configuration or not. And the underlying idea is that the number of variables on which each of these m constraints depend on is relatively small. It should be sort of a small number with respect to the total number of variables. I will give some examples in the next slide, so it might become clearer right now. And well, the first thing you can define with these two ingredients is the notion of solution, and the solution of such a problem is just a configuration of the variables which satisfy simultaneously all the constraints, if it exists, of course. It's not granted all the time. So let's be concrete and let's consider some example. So maybe the first one to picture, and one which is very well known, is the problem of coloring of a graph. So in this case, the alphabet of the variables has q elements. Think of it as q colors, and these variables live on the vertices of a graph. So each vertex in a configuration is given a color, and the constraints live on the edges of the graph, so they only involve two variables at a time, even if the graph is very large. And the constraint is that the two colors on the end vertices of the edge should be different. Okay, this is what defines what is called the proper coloring of a graph, is a coloring which, with no monochromatic edges. And in this case, a solution of this problem is precisely a proper coloring of the graph. The two next examples, which I would like to introduce now, take Boolean variables, work on Boolean variables. And in the two cases, each constraint depend on a subset of k of the variables in the problem. The first one is the famous satisfiability problem, and the constraint imposes that the disjunction of k of these literals has to be true. So let me rephrase it in different ways. So a literal is either one Boolean variable or is logical negation, and disjunction means logical or. So in other words, you have out of the 2 to the k configuration of the k variables on which the constraint acts, out of these 2 to the k variables, there is one which is bad, and that does not satisfy the constraint, and all the other ones are okay. The 2 to the k minus 1 other configuration of these k variables are fine and are satisfying. This is a famous satisfiability problem. There is a twist on this problem, which is called the XOR satisfiability problem, where instead of logical OR, you use logical exclusive OR in such a way that true exclusive OR true is false. And in this case, you can also think of this as variables which, instead of true and false, are 0 or 1. And this operation of XOR is becoming the addition of 0 and 1 modulo 2. So this is just a set of linear equations modulo 2. Each constraint is one equation on this subset of variables. And it also can be seen as a parity check, which are well-known constructions in error-correcting codes, because each of these constraints impose the parity of the number of true or false. And in this case, out of the 2 to the k configuration, you kill half of them. There is only one half which has the good parity of the number of 0 and 1s. Okay, so given an instance, so a set of constraints on such variables, well, as you know, there are many questions that one can ask. The first one is whether the set of solution is empty or not. So whether there is at least one configuration of the variable which is able to satisfy all the constraints at the same time. And this has a yes/no answer, obviously. But there are other problems that you can ask with given the same set of constraints. For instance, you can ask what is the number of such solution, and the answer is not yes or no. Now it has to be a number. Or you can also ask what is the maximal number of constraints that you can satisfy simultaneously. So if the problem is satisfiable, then the answer will be m, the total number of constraints. But otherwise, you have an estimate of how bad you will do if you take the best compromise, knowing that you cannot satisfy all the constraints at the same time. Okay, and in this kind of problems have been, of course, the subject of theoretical computer science, and in particular of computational complexity theory. And in particular, if one focus on the first version of the problem, that is the yes or no question, is there at least one solution of the set of constraints or not? Well, for the K-exclusive OR satisfiability, as I mentioned, it can be seen as a system of linear equation for which you can use Gauss elimination algorithm. So it's an easy problem, a polynomial problem for any value of this parameter K. But on the other hand, the K satisfiability or K coloring problem that I mentioned are difficult, or more precisely are in fact NP complete. As soon as the number of colors for the coloring problem or the arity of the constraint for the satisfiability problem is larger than 3. And actually the satisfiability problem was the first one to be proven NP complete in 71. Let me just say that for a given problem, it can be that one version of this question is easy, whereas the other can be very difficult. So I think there's something which is important to keep in mind. In particular, for the XOR satisfiability problem, it is indeed easy to decide whether or not there are solutions using Gauss elimination. But finding, when there are no solutions, finding an optimal configuration, maximizing the number of constraints which are satisfied, is actually a very difficult problem. And it's even a problem which is hard to approximate within any non-trivial ratio. There is a precise theoretical computer science statement about this hardness of approximation. So difficulty is not only problem dependent, but version of the problem dependent. So there is one criticism, so to speak, or one limit of this beautiful theory of computational complexity is that it's a worst-case notion. So a problem will be declared out of the polynomial class of problems as soon as there is one instance that no algorithm is capable of solving in polynomial time. But maybe most of the instances are easy, and only a few of them are hard, and these are the few, maybe irrelevant examples which make them NP complete for the worst case classification. So one would like to have a notion of typical complexity of such problem. And there are different approaches to this notion of typical complexity. The one I will follow here is corresponds to taking a random ensemble of instances, and so introducing probability in the game, and saying that something is typical if its probability goes to 1 in the limit of large problem sizes. And there are a very simple way to produce a random ensemble of such problem instances. So for instance, in the case of the coloring, you can say, okay, I have n vertices, and I want to construct a graph with some number m of edges. Well, the simplest thing you can do is just take uniformly at random these m edges out of the n choose 2 possible ones. And actually, that's a construction which is known in mathematics under the name of Erdős-Renyi random graphs. And the study of this discrete mathematical structure started in the 60s with the work of Erdős and Renyi. And this kind of random construction can also be generalized easily to the two other problems that I introduced. The only difference is that instead of edges, you have to choose hyper-edges. That is, instead of an edge is something which links two variables, and here you choose something which links k variables. But again, there are n choose k of such objects. You can just draw m of them at random. And it turns out that the interesting regime is always an asymptotic regime. So even in the worst case computational complexity, there is also always it's always understood that one speaks of very large problem sizes. And here, the interesting regime is also with very large problem sizes and with the number of constraints, which is proportional to the number of variables. So I will denote alpha, this ratio of the number of constraints divided by the number of variables in in this limit. And this, well, just provides, I mean, in one sense, a set of benchmark problems on which one can test algorithm. Actually, to make to put this in a historical perspective, it turned out that I mean, in the 90s, people realized that the problems that they knew were NP-complete, like coloring or satisfiability. So it was proven since the 70s that these problems were very hard, but the researchers in computer science faced a rather paradoxical situation that all the instances on which they could benchmark algorithms were easy. So it was very paradoxical, but they knew that from a worst case point of view, these problems were difficult, but they had no explicit examples of hard instances. And it turned out that this construction provides the first natural examples of such really hard instances. To paraphrase the title of one paper of 91, actually. So to study this random problem, the one quantity that one can define is the probability that such a problem drawn at random with so a certain number of variables and alpha times this number of constraints has solution. There is a first trivial observation is that this probability will be decreasing with the ratio of the number of constraints with respect to the number of variables, because the more constraints you put on the system, I mean, you can only destroy solution. It's not by adding constraints, you cannot create new solutions in a problem. So this will be decreasing. There is a slightly less obvious observation, which deserves 2 lines of computation to be proven rigorously, is that for all these problems, there will be a value of alpha fixed, so which does not scale with n, such that the limit of this probability is going to be 0 in the large size limit. And this can be done using Markov inequality or first moment method from discrete mathematics. It's a very simple proof.
Are we talking about the probability of polynomial solution to the decision problem?
No, solution of the problem. I mean, yeah. And here is true for all the examples I've introduced. So of course the details or the value of alpha that one has to take and the value of the probability will be different, but this pattern will be true for all cases. And here probability is probability of existence or not of a solution, whether it can be found easily or not. This is I'm not talking about for the moment. I'm not talking about algorithmic properties for the moment. Well, if you can wait 1 or 2 slides, the answer is coming. Other questions? So actually, the answer is coming. So okay, let's look at these graphs. So which I stolen from some papers. So unfortunately, I've stolen them from a paper. What was drawn was not the probability of satisfiability, but the probability of unsatisfiability. So look at the left diagram and just reverse it to have the quantity I've defined before. So as you see, it's decreasing or increasing in this. So this is as a function of alpha, the parameter I introduced. So, and you see that for large value of alpha, okay, on this scale, it goes to 1 when the size of the system increases. So the different curves are for different system size, this different number of variables. The non-trivial observation is that indeed there seems to be a threshold. So that for a certain value of alpha, in the limit where the size goes to infinity, the probability that solution to this in this problem instance either go to 0 or to 1, and there is a sharp threshold between the two. So that's, for physicists, that's of course very reminiscent of a phase transition, or it's also a threshold phenomenon as there are many also in discrete mathematics and in random graph theory. And to come back to the historical note I was making about the fact that people had hard times finding hard instance of hard problems. Well, then it turned out that if you look at the plot on the right, is a measure of the number of steps that some algorithm has to make to answer yes or no to this decision problem. And without entering into the details, you see that there is a peak, and this peak is more or less at in the region where there is this threshold phenomenon. Because for very small value of alpha, the problem is under constraint, so it's rather easy to find the solution. For very large value of alpha, the problem is very much over constrained, and so it's not easy to show that there are no solutions, but it becomes easier in a sense than when there are a lot of when the problem is strongly over constrained. And so this was one way to, for experimental computer scientists to generate hard instances, well, to generate them close to such a phase transition. So let me rewrite more precisely what I said about this threshold phenomenon. So from the point of view of rigorous mathematics, this is a conjecture at the moment, so that there is a threshold value of alpha, which of course depends on the problem considered and on the parameters k or q of the model, but which separates in the thermodynamic limit either instances which are with high probability satisfiable and others which are with high probability unsatisfiable. Okay, so this has been these problems have been the subject of a lot of works in mathematics and theoretical computer science. I will not enter into the details of all the things which have been proven because it would take a very long time. But okay, there is a weak version of this conjecture with a possibly n-dependent threshold, which has been proven by Friedgut, and there are a lot of upper and lower bounds which have been derived on this threshold. And also there is one simplifying case is when the parameter k, for instance, goes to infinity, but after the n going to infinity, there are also some simplifications which are allowed. Yes.
I was surprised that this is one-sided. The satisfiability phase transition happens only in a certain region. So shouldn't it be like alpha when alpha is smaller than a certain value, then this limit should go to 1, and then in between, that's where it's hard, where it would go to 0, but then you pointed out, if it's highly over-constrained, then it should go back to 1 again.
No, but this is a probability that there are solutions. So if it's over-constrained, there are no solutions. This is not an algorithmic statement. It's just a structural statement about the existence or not of solution. So okay, if you want more details on this pattern, so in the large alpha regime, it's always exponential with the size of the system, of the number of variables, because this is a rigorous result that we don't know how to do better than resolution proofs, and resolution proofs for this is exponentially large, and but with a prefactor which goes like 1 over alpha at large alpha, But again, this is just a structural statement about the absence of solution at just large enough value of alpha, not alpha infinitely large. Okay, but okay, there are a lot of very nice rigorous results on these problems, but there are at least two things which are not completely satisfactory. The first one is that there are no explicit prediction for this threshold at finite or small values of this parameter k. And also, up to a certain point, all the results obtained rigorously didn't really point out why there was something difficult happening for values of alpha slightly before this threshold, and that's where I think the use of statistical mechanics methods proved to be quite important and to bring new results and a new perspective in this field, and that's why I would like to spend some time on this now. So the first question is what has physics to do with such a problem? And again, here, depending on your background, either you will find this completely trivial or completely cryptic. I'm sorry, but in a nutshell, what statistical mechanics does is to introduce some configuration space, which is supposed to be a microscopic description of a physical object, but you can abstract from it and say that it's just a model, which is given by a set of configuration made of a lot of microscopic degrees of freedom, on which you define something that we call energy when you are a physicist. And we introduce a parameter that physically is called the temperature. And then, following the fathers Gibbs and Boltzmann, we introduce a probability distribution over the space of configuration, which is up to some normalization factor proportional to exponential of minus the energy of the configuration divided by temperature. Okay, that's the prescription of statistical mechanics. And now the traduction with combinatorial optimization is rather simple, because if you think that the energy of a configuration corresponds to the number of unsatisfied constraints of your constraint satisfaction problem, and if you look at the limit of low temperature, at low temperature, so this 1 over T will become very large. The exponential will be very much peaked on the minimal values of the energy, and it will concentrate, this probability measure will concentrate on the lowest energy configuration, which are precisely the ones solving the optimization problem because they maximize the number of satisfied constraints. So in some sense, this is exactly actually the same problem if I formulate in this way. The only difficulty with respect to usual statistical mechanics is that here we have some randomness in the definition of the problem, so some randomness in the energy. And this is not the usual setting for one part of statistical mechanics, where we consider ordered systems, translational invariant systems in finite dimension, for instance. But there is a branch of statistical mechanics which deals precisely with disordered systems, and in particular with a class of systems which are known as spin glasses, and which actually correspond precisely to this kind of random optimization problem. And here, the fact that in the definition of the instance, there was no reference whatsoever to some finite dimensional Euclidean lattice, so the edges in the random graph coloring were chosen uniformly at random among all the possible pairs, makes it what is called the mean field problem in statistical physics, and this is a good news. Even if you don't know what it means it's that we have more powerful methods and that the problems are easier in general in this mean field setting than in finite dimensional problems. And one simple example of this translation for the graph coloring is precisely what is called a Potts model. So that has q possible values for each spins, and with so-called antiferromagnetic interaction, because the constraint tends to put the spins in different directions. They don't want the colors to be the same on neighboring vertices. Okay, so there is a link with statistical mechanics. So there is a hope that statistical mechanics techniques can bring result, and it has indeed been the case, because here I'm telling a story which started a few decades ago. So I present it as a new story, but it's not. Okay, and in particular, there has been different outcomes of this line of research in this precise case of random constraint satisfaction problem. So one of them has been quantitative estimation or conjecture on the value of the threshold for the satisfiability. But maybe that's not the most important part. I mean, I think that the most important part is that it gave or it relied on a very much refined picture of what is going on in the satisfiable phase. So before the satisfiability threshold, so when there are still solutions, actually there are a lot of action going on in this phase, and that's what statistical mechanics revealed. And it also had some consequence also for algorithms with the introduction of techniques from out of equilibrium physics to analyze some algorithm, and also to propose new algorithm like survey propagation, for instance. So I will try to give you some ideas about some salient feature of these outcomes now. Okay, so maybe that's the one main message that I would like to convey is summarized in this slide. So let's browse through it slowly. So by definition of the satisfiability threshold, for alpha smaller than this value, there are solutions. And not only that, it's not too hard to see that there are exponentially many of them, with a rate that physicists call entropy, this function S of alpha. And this is, I mean, that it's exponential is natural because the size of the configuration space is 2 to the n or q to the n, so it's exponentially large. And at very low value of alpha, there are very few constraints, so essentially all the configuration space are solutions. And adding constraints, you put holes inside this configuration space, so there are less and less, but they remain actually exponentially many with a slower rate of growth, but still exponentially many up to the satisfiability transition. The important point to realize is that something happens before this satisfiability transition, and it's a transition of a different nature, which corresponds to a clustering transition. So what I mean by that is sketched on this plot. So the problem with this drawing is, of course, a very coarse simplification of what is going on, because solutions are in the hypercube of 2 to the n points. And so it's very difficult to draw it on a plane. And well, of course, obviously it's impossible. So there are only sketches. But what this sketch means is that for low enough value of alpha, this exponential number of solutions are scattered more or less regularly inside the hypercube of all possible configurations. And they are well connected one with the other. So if you take any two solutions for alpha smaller than this alpha d, you can go from one solution to the other by a path which only goes from solution to solution. And on each step of this path, you move in Hamming distance something which is relatively small. Let's say at least not extensive in the not proportional to the number of variables itself. So it's well connected, so to speak, this set of solutions. On the other hand, when you go above this clustering or dynamic transition, what happens is that it's not true anymore. And there is a breaking or shattering of this the set of solutions inside the hypercube, which gets a non-trivial organization in clusters. So there are some groups of solutions which are close to each other and which can be connected in the way I was telling before, but there are pairs of solutions which are disconnected, or pairs of clusters which are disconnected one from the other. So at some point there is a notion of connectivity in the space of configuration which breaks down. Okay, is this clear more or less the idea of this sketch? And so not only this, but the number of the total number of solutions, as I said, is exponentially large, and this entropy actually has to be, has two contributions. One coming from the number of clusters, which is exponentially large in this regime, and another one coming from the number of solutions inside one cluster, which is also exponentially large. And the crucial point is that the characterization of the satisfiability transition is not that the total number of solutions disappear, but it's that the number of clusters disappear. So at the satisfiability transition, what happens is that the last cluster dies, but before dying, it still contained a very large number of solutions. And in other words, to compute this satisfiability transition, one has to understand this before, because if one does not try to separate this contribution of the number of solutions in these two very distinct contributions, one cannot find this point as the point where the number of clusters disappear.
These two equations for the number of clusters and number of solutions within a cluster, that is in the state where alpha is between alpha sub d and alpha sub s?
Exactly. Before alpha d, sigma is 0. There is a single cluster if you want. And all the internal entropy correspond to the total entropy if you want. Actually, I will show a plot.
Is it known whether if you look at strings that violate just one constraint, so not in quantum physics lingo, not the ground state, but the guys who are in the first excited state, are they organized in a similar fashion?
Yeah, this persists at positive temperature.
Because that would cast the discussion of the minimal gap in a quite different light. And actually we saw this, such an organization experimentally, that I was asking in the machine learning. Sort of the different solutions came in groups and in bands of energies that were separated. So if you're in a situation where you're just left with a last ground state cluster or a few, then maybe the question, as long as I find one of these solutions in the cluster, I'm happy. I don't want to go up to a cluster that represents violators of one constraint. So it's the discussion then becomes, well, what is sort of the gap between those clusters, the energy gap between those clusters?
Yeah, well, at the moment it's everything classical. So here it's really, gap is just classical energy, just flipping variables. So it's not maybe the most interesting case. Well, the gaps that you encounter when doing a modification of the transverse field on such problem will be much interesting. And this, I hope to speak about at the end, but. Okay, I will try to rush to it if you want to hear about it. Otherwise, we will discuss it later privately, I guess. Okay, so just to show and to answer maybe more precisely one question, there is on the case of this XOR satisfiability on a random hypergraph, all this can be made very precise, very rigorous, and here the clusters can even be characterized with a very simple, so to speak, geometric argument as with the notion of core of the hypergraph of encoding the formula. So this is the the upper line is the total entropy of solution. So the total number of solution is exponential. I mean, it's 2 to n times this factor. And in this regime between alpha d and alpha s, it has to be decomposed between this contribution of the degeneracy of the number of clusters, sigma, and the internal entropy of each cluster. Well, actually, for satisfiability and coloring problems, this picture is even more complicated, and I will come back to it maybe later on. I will try. Okay, so I don't have much time, so maybe I will just try to flash this on the next slide to give you a little bit of the idea of the methods which have been used to obtain quantitatively this picture. So there is in particular a method called the cavity method, which relies on the following observation. So one can define the uniform measure of the solution as a product of these constraints, which are, as you recall, 0 or 1, whether they are satisfied or not. So this factor, this product of constraints is 1 if and only if all the constraints are satisfied. So if the configuration is a solution. Then you normalize, and you have the uniform measure. This kind of probabilistic object can be encoded or at least represented graphically by something which is known as a factor graph. And a very small example is shown here, where one puts, it's a graph with 2 types of variables. So here cycles are used for variables, so x1, xn are drawn as wide variables, and each constraint is a square vertex, which is linked to the variables on which it depends. And so this is a very nice graphical representation of the problem, and a crucial property of these random graph models is that typically the random graph encoding such a random constraint satisfaction problem locally converges to a tree. In other words, there are locally no small loops around no vertex in such a graph. And this is a crucial property because maybe, as you know intuitively from a coding point of view, trees are very nice and simple objects because they have a recursive structure. And so if you want to solve a problem which has a structure of a tree, usually if you break it in subtrees, you solve the problem on the subtrees, you combine the solutions, and then you have a very efficient algorithm, so which is what dynamic programming is about. And in this context, it's also known in artificial intelligence or machine learning community as the exactness of the so-called belief propagation algorithm on tree structures. So it seems at this point that the situation is very easy because I said that the constraint satisfaction problems have factor graphs which are locally trees. I just said that trees are trivial objects. So it should be always trivial. Well, no, actually, because the fact that the trees converge locally that the graphs converge locally to tree is not sufficient to avoid some problems of lack of correlation decay. So these are rather technical points, but the fact that that the clustering transition actually can be related to the absence of some correlation decay in for the variables in this factor graph measures, and if the variables have long-range correlation, you cannot forget about the long loops that you try to forget when you just take locally a tree. That's the crucial point, which is behind this the fact that these models are non-trivial and allow for such a clustering transition. Okay, I don't really have time to enter too much into the details, but so I will just go on, but just try to emphasize this fact that it's really local convergence of random graphs to random trees, plus some, in some cases, very complicated but self-consistent hypotheses on what are the boundary conditions, the typical boundary condition on the graphs, which effectively take care of the effect of the long loops. That's the main characteristic of this so-called cavity method. So as I said previously, this clustering transition actually is not the end of the story, and for case satisfiability and q-coloring, it's even more complicated. Because, okay, as you see at alpha d, I've drawn the set of solutions to be shattered into many clusters. But it turns out that there is a further transition called the condensation transition between this point and the satisfiability one, where the number of clusters which bear the vast majority of the solution is exponentially large, actually only between alpha d and alpha c. And for the latter regime, this condensates onto a small number, a sub-exponential number of the largest of the clusters. So, okay, just to say that, I mean, the details of what is going on is very much model dependent, because, for instance, in the XORSAT model that I shown before, there is no intermediate phase, and the last two thresholds are equal to each other. And also for satisfiability, the case and coloring, the case k or q equals to 3 is again as a special feature. So the main message here is beware. I mean, the devil is in the details, and sometimes the details of the model do really matter, and so one should not try to generalize too easily too quickly what is obtained on one model on the whole class of model. And finally, at this point, I will just mention that all this, I mean, from a mathematical point of view, all what is done by or good deal, which what was done in statistical mechanics was not strictly rigorous. I mean, it's theoretical physics style of computation. But the good news, and that's what makes this field of research very, very rich and very interdisciplinary, is that a lot of this prediction is at the moment proven step by step rigorously by mathematicians. So which gives more credit to the predictions, I think. Okay, I'm starting the quantum last part of it. If in, I don't know, 5 minutes or? Okay, no, 5 minutes will be fine. No, I'm just kidding. So quantum models are, I mean, in a very simple and non-physics way, are, okay, suppose that you have Boolean variables, you have 2 to the n configurations, which have some energies or cost functions, and you put them on the diagonal of a matrix, a 2 to the n per 2 to the n matrix, and you add some off-diagonal terms, which represent jumps between configurations. And okay, the precise form here is given by a transverse field, so if you know what it is, it's okay. Otherwise, just think that there are some off-diagonal elements that are added to the classical energies of the configuration. And now, well, what corresponded to the energy or cost function of the classical part become the eigenvalues of this matrix. And so that's the question of the properties of the spectrum of eigenvalues of such a matrix. And so the question is, we have seen a lot, and I said that there are even more phase transition typically in the structure of in the classical structure of these models. And so, well, what happens of all this phase transition, for instance, as a function of the transverse field, the transverse field gamma? And well, obviously, this well, one motivation for this question is to understand whether, I mean, what happens if one tries to make a quantum annealing to find to solve this kind of optimization problems. So, as I say, these models are mean field spin glasses, and at least in the regime where, well, the so-called fully connected regimes where all variables interact with each other, this has been well studied in physics since the 90s. So what we have done with collaborators in Paris was to make an extension of the cavity method that I explained very briefly to quantum models of this type. And the idea of this is based on what is called a path integral representation of such quantum models. So this horrible formula essentially tells you that instead of if you have some cost function and instead you want to compute the eigenvalues of the operator where you have added some of diagonal elements, you can do this by somehow replacing the variables. So, for instance, the Boolean variables by function, which are Boolean variables depending on some imaginary time, very imaginary, and you modify a little bit the cost function on this new space of configuration, and somehow you manage to get the information you want on the spectrum of the new operator with quantum fluctuation. And so as essentially the topology of this new model remains the same, if, as I said, what was crucial for the cavity method was the local convergence to trees of the random graphs, and this remains the same for the quantum version of the cavity method, so it can be extended at the price of handling a lot of technical difficulty from going from Boolean variables to time-dependent Boolean variables. But this allowed us to study in particular a model where there was this replica symmetry breaking, or this phenomenon of clustering in presence of a transverse field. So, as I said already, in the classical case, there are many different detail-dependent, model-dependent details, and in the quantum case, it's only getting worse. But there are so one has to study example by example before trying to draw any general rule. So I will just talk about two examples. So the first one is this problem of Boolean equations. So this XORSAT satisfiability. And here you can see what happens as a function of this transverse field gamma. So gamma equals to 0 was the classical case. And here it's for graph which have a special regular structure. And so, okay, the only thing here that can be seen is that there is a so-called first-order transition as a function of the transverse field. So there are two energy levels which almost cross but do not exactly cross, and which induce an exponentially small gap at the transition. And this is one effect that can happen in a subclass of this class of random constraint satisfaction problem model. And so this is one possible phenomenon in this case. And there is another one which concerns not what happens at a phase transition, but really what happens in a whole range of low values of gamma in a spin glass phase. And here there is a possibility for something which is a whole gapless phase, so a continuum of very small gaps for a whole range of values of gamma. And this we found in a toy model which were with a phenomenon of crossing induced by a competition between entropy and energy of the different clusters. And we have also good evidences for that this mechanism is also at work in a more realistic version problem, which is precisely this coloring problem in presence of transverse fluctuation. Okay, I think my time is over, and I thank you for your attention.